Good morning. My name is Emanuele Di Lorenzo, and I'm a professor and director of the program in Ocean Science and Engineering at the Georgia Institute of Technology. And today I'd like to spend a few minutes talking about this Savannah water integrated tool for ocean, coastal, and river hydraulics forecasting, which we have termed the SWITCH model. Now, this is a collaboration that has many people involved, including a European center, the Center for Mediterranean Climate Studies and Change. And here are listed some of the collaborators: the University of Bologna, Dr. Nadia Pinardi, and from Georgia Tech, a PhD student, Kyunjimin Park, who is primarily responsible for this work. And I think he's in the room today, so thank you, Kyunjimin. So why do we have a model? The goal of this project is really to model and forecast water level changes at the scale where people live. And here's an animation showing the model domain, where we actually do the computation and integration. And this is in particular, you're looking at the water depth, different scales. And as we zoom in, you can see that the model is able to capture changes in the water at the scale where exactly people live. And this is downtown Savannah. And in particular, for the city of Savannah, the resolution inside the channel here is about 10 meters, which allows you really to capture all the variability in the channels. Now, the model, of course, needs some input or some boundary conditions to run the models, or forcing that come from large-scale ocean and weather forecasts. And these include variables such as tide, winds, ocean currents, sea level, temperature, salinity, and many other variables. And what you're seeing here is just an animation of water level anomaly in meters for a particular period of the model integration. And so you can see the tides coming in and out in this particular instance. Now, of course, in the coast of Savannah, we have lots of rivers, and those are really important because they provide fresh water that comes down from the rivers into the coastal ocean. And so in particular here, we also use data and forecast data from the National Water Model, which is a US-based model that provides essentially river runoffs. And here are some of the rivers that are included in our model. And you can see in this animation how the fresh water, depicted here with the blue color, is coming down the river, and it gets entrained in the circulation of the coastal ocean and produces these plumes that are fluctuating, oscillating back and forth with the tidal cycle. So using this model, at this time we have an automatic system that provides real-time 3-day forecasts. And I want to provide you just a quick example overview. This is the website where these forecasts are posted. And at this website, you will be able to find things like currents, temperature, salinity, sea level, and you can use this interface to zoom in particular regions. And here I wanted to just have a chance to introduce a zoom in the Port Pulaski region, where we have at the mouth of the Savannah River a tide gauge. And so this is essentially the circulation at Fort Pulaski for a particular time. This was, I think, 2019, May 16. And we can look at the tide gauge at Fort Pulaski, which is plotted here as a time series of sea level in black. And these are real observations. And in red is the model hindcast or monitoring, and as well as the forecast that you see in the future. And you can see that the model has a high fidelity in capturing this particular tide gauge, along as the other tide gauges that are now installed through the sea level sensor network. But we can do more. Of course, a primary interest here is coastal flooding and hurricanes, and we had some recent hurricanes that passed along, and so I want to spend a few words about that. So again, this is the model at the large scale, if you like. This is the coast of Georgia and Savannah, and this is a model that we call the state level grid. It covers the entire coast here, and the resolution here in the outer water is between 1 to 7 kilometers. And we can use this model to also understand and possibly predict flooding events associated with extremes like hurricanes. And the way we do that is, if we zoom in, this is essentially a city scale resolution at 10 meters. Again, this is downtown Savannah, and this is sea level variability in a normal day. And the model allows also to predict flooding. So if we actually increase the sea level through a storm surge or an inundation event, this is what the model is capable of reproducing. And so this is an example of a scenario where we artificially inundated Savannah, and you can see that the water spreads in the city. And so we want to use this capability of the model to capture these inundation scenarios to really try to understand impacts of large extreme like hurricanes or other extreme precipitation events. So let's talk about the recent hurricane. This is Hurricane Dorian. And what I'm showing you here in this blue map is essentially a map of the sea level pressure and wind speeds that are associated with the hurricane as it kind of brushes through the coast. Down below here is a time series of the sea level at Fort Pulaski. And you can see here in magenta, these are the actual observation. And the yellow period here, this is the time when the hurricane kind of hit the coast. And what was really good about this hurricane is that the sea level didn't really go very much. It didn't grow very high. There was no real coastal flooding. And in fact, after the hurricane, the sea level tended to be lower than usual, as you can see in the tidal cycle. The interesting news is that the model was able to forecast this type of response to this hurricane quite well here in black, which really built our confidence that this model is capable perhaps to capture these large storm surges. However, of course, Dorian not having a flooding event wasn't quite an exciting case for us to study. And so we went back and looked at Hurricane Matthew. And so here again is an atmospheric kind of evolution of the hurricane. You see brushing on the coast in the same way as Dorian did. And now we can actually look down here to the actual sea level. And the yellow box here represents the time period when the hurricane actually hit the coast. So let's start by looking at the magenta line. The magenta line is the observations, and if we look at the observations, we had a big peak with over 3.5 meters of sea level, and we know there was a lot of coastal flooding during that time, during the hurricane, and then a big drop returning to normal condition. What's interesting is that large-scale kind of prediction system, this is in a European one in particular, in green, the green line, didn't quite predict the level of flooding that occurred in the Savannah area. In fact, it didn't predict it at all. Whether our model, the switch model, was able to capture this large flooding event, as you can see here with the black line, and then the return to normal. So this gave us some confidence, and in fact this model can be a great tool to study the effects of hurricane on these coastal flooding, but also predict them. Now, why did the large-scale forecast didn't successfully capture this big event in flooding? Well, the reason stands here in this map. This is a map of the highest sea level that was experienced during the Hurricane Matthew. And what you can see along the coast is that there's a lot of regional spatial structure, or if you like, non-uniformity in regions that get very high sea level versus regions that don't get very high sea level. So this is to say that in order for us to really understand how coastal flooding patterns emerge, we need to have a high-resolution model that can capture these kind of spatial dishomogeneity along the coast, in particular in the sea level. And so this gives us a lot of confidence. Now, a good question for scientists is, if we look, this is a map now, an animation that shows the arrival of these hurricanes on the one side Matthew and on one side Dorian, and this is mean sea level pressure. This is the atmospheric counterpart of these hurricanes. And if we look at this evolution, and let's just play it one more time, let's see if we get another hurricane here to come, we see that the track of these hurricanes was quite similar. In fact, let me go backwards. This is one track, you can see it here, and let's stop it right there, and then we can go on this one here again. We can see the track, and this is at the peak of the hurricane. And essentially these two hurricanes had very similar track. And so the question really is, why we had a hurricane that had similar track, but then it had such a big difference in the flooding that we experienced at the coast. And so what turned out to be the case, that we found that in particular during Matthew, there was this big storm of precipitation that happened, over the coast of Georgia. And you can see it here. This is in October 6 of 2000, I think. I don't remember the exact year right now. But you can see there's a peak in the precipitation, and that is captured by gauges at both the Savannah and Ogeechee River. And this precipitation actually had a big impact downstream in terms of river discharge, which is plotted here with the blue and the red line. Now, this type of precipitation extreme and discharge did not happen in Dorian. And this is an important component because it really turns out that the combined effect of precipitation extreme and storm surges together are really important in capturing these coastal flooding events. It's not just about the hurricane hitting the coast, but we actually have this compound effect of different processes. And the model allows us to combine and capture these processes all at once. And here I'm mentioning precipitation extreme, but actually further studies show that there are also other conditions associated with the offshore ocean circulation in the Gulf Stream that have an impact on the sea level and the flooding that you get during one of these events. And so with that said, it becomes important for us to continue to develop a regional modeling capability. We call it the regional Earth system model, to really integrate these coastal models like the one I showed you today with atmospheric regional models that allow us to also model the land hydrology and forecast, even with more accuracy, the input of rivers and other precipitation events. And ultimately, the goal is to combine the output of these kind of regional Earth system models with local urban flooding models that have also infrastructure, and those will allow for studies of how to build more resilience infrastructure in the face of more coastal flooding events. And so ultimately, all these modeling tools, combined, allow us to understand the interaction between these different components: the water, the air, the people. And most importantly, they provide some quantitative basis to develop something like a smart coastal area resilience planning tool that could be useful for managers to really do a better job at managing all these emergencies. So with that, I want to thank the Kim and the other organizers for allowing me to speak here. And again, if you have more questions, please feel free to ask Kyungyemin Park, who's here in the audience. Thank you very much.